All right, we're still in section 2, and we're going to talk about one more way to find volume, which is using a known geometric shape as a cross section to kind of fill the volume. So let's look at a problem, and then I have another one of those cool little GeoGebra simulations to look at. So it says find the volume of a solid formed by revolving the region bounded by the curve of x squared plus y squared equals 9 and the x-axis about the x-axis. So this is kind of what we've been doing using just our disk method. So, okay, we have the curve x squared plus y squared equals 9 and the x-axis. So we're talking about the top half of that circle that has a radius of 3. So it would be, here's our graph. We're looking at this region. We want to rotate it about the x-axis and look at that solid that would be formed, so kind of that egg shape. So the way we've been doing this is to use a representative rectangle, connect it from the function to the axis of revolution, and come up with our volume. So R should be, now I can't have it as x squared plus y squared equals 9. Since this is a vertical rectangle, I need everything to be in terms of x. So I need to solve this equation for x. Solve it for y so it's in terms of x. And if we just square root both sides. Now we get plus or minus, but we're talking about the top half of the circle where all of the y values are positive. So R is just the positive square root of 9 minus x squared. And when we do the volume, it's pi times the integral from the x limits, which are negative 3 to 3, of r squared. So I'm just going to write 9 minus x squared dx. And in interest of time, because I don't have much of it this morning, we can solve that with or without a calculator, right? This is easy to integrate and fairly easy to get the answer to. I will show you here's my exact answer if we were to go through the actual work. So what if instead of each slice being a disk, what if we used other shapes like squares, triangles, semicircles? So it is kind of hard to visualize this. So let me just show you what we're talking about. Well, let's read this problem first, and then I'll show you what we're talking about. So a solid has a base in the xy plane bounded by the graph of y equals square root of x. So this is the base of our solid, square root of x, y equals 0, and x equals 9. So this little chunk here is the bottom of our shape, the base. Find the volume of the solid if every cross-section by a plane perpendicular to the x-axis is a semicircle with a diameter on the base. So if you're trying to sketch this, it's like, look at this first one. Let's say here's this first one out here. There'd be some sort of a semicircle, and it's hard to sketch this to make it look, correct. There'd be one there. There'd be an infinite number of these things. Instead of rotating this at all, we're just making a bunch of these semicircles. Now, I'm not the greatest artist, and so this is not really doing it justice, but that's what I found this cool little simulation. So let's do semicircles. This is not, here's the base of this graph, whatever this one is. And let's just say we're going from 0 to 1. If I generate a bunch of semicircles, you get this sort of cool looking dome shape. This is what we're saying, right? And the more semicircles we have, the more this will fill in. Ultimately, we want an infinite amount, so we'll use an integral. All right, we can also do this with equilateral triangles. You can see those filling in. See how it kind of becomes the same shape in the end? It doesn't quite matter what the shape is. You're getting similar volumes. They're not all going to be the same volume, but they all generate this sort of cool domey type shape. All right, so anyway, back to our problem. We're looking at semicircles. So find the volume of the solid if every cross-section by a plane perpendicular to the x-axis has a diameter on the base. So the volume in general is going to be the integral from the x value 0 to 9 of the area, in this case, the area of a semicircle, area of our semicircle, times whatever the thickness of that semicircle is. So, each of these, I drew these little like slices here. The thickness would be dependent upon how many semicircles you're putting in. So when we say thickness or width or whatever, we're really just talking about putting a dx in here, or like in our previous notes, we said w or delta x, and we changed that to dx. So the real work in these problems is figuring out, wait, what is the area of this particular semicircle? Now, I know in general, it's 1/2 pi r squared. The question is, what is r? Okay, so let's keep working on this. It's 1/2 times pi. What is r in this case? The diameter of the semicircle goes from the top of the function down to the line of the x-axis. So we can think of this as like still a top minus bottom situation. All right, and so we can still think of that just like we've been doing with area and volume previously. We can say, all right, well, on top is the square root of x function. And on the bottom, this axis, or the, not how I almost said axis of revolution, this x-axis right here is just 0. If we were connecting it to the line like y equals -2, then that would be minus -2. All right, so the area of a semicircle in this particular shape is going to be pi times square root of x over 2, if I simplify that. All right. Oh, wait. Sorry, what am I missing? Squared. Goodness. And